Alrighty, I'm shooting for a 20-minute video. Let's see how I do. So we're going to talk about periodic trends. Obviously, you're going to need a periodic table. You also need to understand how electrons are organized into SPDF sublevels and energy levels like 2s versus 4s, and how those prefixes represent the energy level that electrons are placed upon. We're going to be looking at ionization energy, we're going to be looking at atomic radius, and we're going to be looking at electron affinity. And if those terms don't mean anything to you, that's because we're explaining them today. All of these terms and concepts can be described using Coulombs Law. Coulombs Law is a measure of the force between two charged particles, and the equations given there, K is a constant, Q1 is a charge, let's say maybe a proton or two. Q2 is also a charge, maybe the electrons in the orbitals. And then D is the distance. Maybe you could think of the distance as the energy level, because the higher the energy level, the farther away it is from the nucleus. So you can plug values into there, and you can measure the force. If the force is negative, if it's a negative value, then they're being pulled towards each other. If the force is a positive value, they're pushing each other away. Repulsion versus attraction. The more protons you have in the nucleus, the more they're going to attract the electrons. And then again, as the distance from the nucleus to electrons increases, the attractive force is going to decrease. So if you think about the protons as being 0.0 in the nucleus, and the energy levels, the first energy level electrons compared to the 4s energy level electrons, the 1s energy level electrons are very close to the nucleus. That distance is going to be small, so the force is going to be greater. The 4s is multiple energy levels away, so the distance is going to be greater, which means the force is going to be less. That's kind of a lot of what we're going to be talking about, is force as in the attractive pull of the protons on the electrons. We could also describe the repulsion between electrons. Let's say that you have electrons and electrons both plugged in for the charge. You'd have a negative and a negative, and they'd be resulting in a repulsive force away. And this comes into play when you have multiple electrons in an atom. If you are talking about an electron on the second energy level and another electron that's on the third energy level, both of those electrons repel each other, and they do exert a repulsive force. The common symbol for the proton is Z, and there is something called the effective nuclear charge. We're going to use this term a whole lot. The effective nuclear charge is the number of protons in the nucleus as compared to the number of core electrons. So not the valence, but the core electrons. And you compare those two, and you have what's called the effective nuclear charge. As we go across the periodic table from, say, potassium to chromium, potassium to krypton, we keep increasing the number of protons, but we're not changing the number of core electrons. So the core electrons are everything that's on the inside, and the valence electrons are those outer energy level electrons. So as we go across the periodic table, we have more and more valence electrons. This is from left to right. We go more and more valence electrons, but we aren't changing the core electrons. We're also, as we go from left to right, adding more protons to the nucleus. So the effect of the nucleus is increasing because you have more and more protons pulling on those electrons. There's two general trends here. As we look down the periodic table, we get more and more core electrons. So we're adding more and more shielding electrons. What does that mean, shielding? So if you have first energy of electrons, and then second, and then third, and then fourth, and they're all being pulled by the nucleus, the third energy level is going to have a greater distance, so that's less force. And what's between the third energy level and the protons? What's between the third energy level and the protons? More electrons. So those electron layers, the first energy level, the second energy level, they're going to be pushing the third energy level away. We call that push, that repulsion from the inner core, we call that shielding because it's pushing them away and it's shielding them from the nucleus. So the inner layer or core shields the valence from the nucleus. That's why it's called shielding effect, because the core electrons are shielding the effect of the nucleus. So as we go down the periodic table, we keep adding energy levels, so the shielding effect is increasing. As we go from left to right, we have the same amount within a particular period. We have the same amount of shielding, but we are adding protons, so the effective nuclear charge is increasing. We actually see that right here in this chart. This is an atomic radius chart. In this atomic radius chart, we see the size of the atoms growing as we go down. And it's growing for two reasons. The first is that we're adding more energy levels electrons. Hydrogen is 1s1. Lithium is 2s1 on its valence. Then 3s1. Then potassium's 4s1. Rubidium's 5s1. Cesium's 6s1. But it's not a linear relationship. It doesn't make a straight line in its amount of increase as we add, because you also have the nucleus can't pull on the valence as well because there's more core electrons. So cesium has a whole lot of core electrons that are repelling that valence shell. So as we go down the periodic table, we're increasing the shielding effect because there's more energy levels, and those outer core electrons, outer valence electrons, are getting farther and farther away. And then the other direction, as we go from left to right, say from sodium to argon, we see the size of the atoms are pretty much decreasing because we're adding more protons, increasing the effective nuclear charge, but we have the same shielding effect. Sodium and magnesium both have 1s2, 2s2, 2p6, and then you get the third energy level. So the 1, 2, 2, 1s, 2s, 2p, that's what's shielding sodium and magnesium's valence electrons. They're 3s. And as you go across, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, all of those have the same core, 1s, 2s, 2p, but the valence are changing, as are the protons. So with more protons, you get more pull. All right, so as we go across left to right, we're talking about the effective nuclear charge changing. As we go up and down, we have to talk about how the shielding effect is changing. Here's a graph that kind of shows that trend, that the shielding effect is decreasing. That the shielding effect is not impacting, the shielding effect is not impacting a particular period, but it does impact when you get to the next period. So as you go, this is the very first kind of weird swoopy line. That is, and let me see, I can draw on here, right? Yeah, this swoopy line here, that is the second period. This is the third period. This is the fourth period. This is the fifth period. And so those periods actually, they're decreasing in atomic radius as you go down those lines I just drew, because you're gaining more and more protons, but you're not changing the core electrons. So as we go down, we're getting more and more protons, so the effective nuclear charge is increasing, and then bam, now it changes. Why did it just jump? Because we added a new energy level, and that new energy level is farther away from the nucleus, and there's going to be more core electron shielding. Repeat, farther away from the nucleus. This entire line I just drew represents the fourth energy level, so that is potassium through krypton. And then again here from rubidium to xenon, sorry, that was a wonky line, rubidium to xenon, we're adding another energy level, which is further from the nucleus and has more shielding. So with this graph, we can see both. We can see the shielding effect. Each line, each group period has its own kind of trend. And then we can also see within the period, there's a slow decrease because we're adding protons. Yes, I do see that there are some aberrations. We are not going to try to explain the aberrations to the trend. Here's pretty much the same thing, just a graph with better numbers. All right, our next thing we're going to talk about is ionization energy. This is how much energy it takes to remove an electron from one of these gaseous atoms to make it into an ion. So it's how hard is it to take an electron? How much energy do you have to put in to bust an electron off? It doesn't take too much energy for metals. It takes a lot of energy for non-metals. And so these values, the kilojoules per mole, is how much energy you have to put in to remove 1 mole of electrons, or 2 mole of electrons, or 3 mole of electrons. And so ionization energy is how hard it is to remove electrons. Similar to the last one, we're going to see different types of trends. The first trend we're going to talk about is called first ionization energy. How hard is it to take the first electron away? How hard is it to take the first electron away from aluminum? How hard is it to take the first electron away from iron? What about neon? What if you just want to take 1 electron? So that's what the first ionization energy is, the energy to take 1 electron. We're going to see a similar trend. We're going to see within a period, there's one trend. Within a group, there's a different trend. And here's the graph, all right? You have the same graph in your notes. It's not yellow, but I think I truncated it just slightly. I think I only showed like this section here. Wow, that's the worst circle I've drawn this minute. So we have a similar trend. We have, here's lithium to neon. That line right there, that's the second period. Sodium to argon, that's the third period. Potassium to krypton, that's the fourth period. So why do we see these trends and then repeat, trend and then repeat? Because from lithium to neon, you're filling up the second energy level. Neon is 2s1. You slowly build all the way up to 2p6. That's neon. Then you get to sodium. That's 3s1. It's a new energy level. That new energy level is going to have more electrons in the core. 1s2, 2s2, 2p6, 3s1. And so you're starting a new energy level, and those electrons that are in the core shield the electrons that are in the valence. Remember, the core electrons shield the valence. There's a separation there. And these are the same two graphs. And so these graphs show how we can have trends as we go from period to period to period, and then also how we can have within a period there is a change in the number of protons. The effective nuclear charge is inhibiting the ability to take electrons. It's also inhibiting the size. I believe in your research chem or your academic chemistry class, we just said smaller the size, harder to take. Well, now we actually have to use the correct terms. We have to say that if I compare potassium and sodium, potassium has a larger atomic radius because potassium has more core electrons shielding the valence energy shell. All right, we have to use the correct terms. If I want to compare potassium to calcium, calcium is going to have a higher first ionization energy. They have the same number of core electrons, so shielding effect is not a case with potassium and calcium, but because calcium has more protons, it has a higher effective nuclear charge, and it's going to be difficult to remove its valence electron. So you actually have to discuss those terms in kind of a essay type manner. And here we are kind of comparing sodium to chlorine. Sodium would be easier to remove, chlorine would be harder to remove. They're both in the third period. So if they're both in the third period, you could ignore shielding effect. You have to say shielding effect is not the reason. Shielding effect is equivalent for both of these. They're in the third energy level. But chlorine has more protons, so it has a higher effective nuclear charge, and it's going to be more difficult to remove electrons from chlorine. Now lithium and cesium. Lithium and cesium are in the same group. Cesium has way more energy levels than lithium, so it's going to be easier to remove from cesium, harder to remove from lithium. Why? Cesium has a whole lot of shielding effect. Each layer of electrons repels the other layer, and so cesium's 6th energy level electrons are going to have a lot of shielding effect on them and be easier to remove. All right, the last question there, which has a larger second ionization energy, lithium or beryllium? This one's probably going to throw you. When you take the first electron off, what's left behind? Well, if you take the first electron off of lithium, you know what? You might want to write the configurations. Here, I'm going to say them real quickly, because if I try to write them, it's going to be ugly. Lithium is 1s2, 2s1. Beryllium is 1s2, 2s2. So let's circle which electrons would be removed. If we're doing the second ionization energy, we have to remove not one, but 2 electrons. So circle the 2 electrons that would be taken from beryllium. That would be the 2s2. Good job. Circle the 2 electrons that would be removed from lithium. That's a bit harder, isn't it? So you definitely take the 2s1 electron, but you have another electron you have to take. That's going to come from the core. So it's going to be a lot harder to take lithium's second electron because it's a core electron. And it's going to have less shielding on it. See? There you go. Okay. Things to say and not to say. Do not say this. Do say this. You can't just state the trend. You have to explain the trend. You have to talk about effective nuclear charge. You have to talk about shielding effect. You can even use Coulombs Law. You can say, you know, because the different energy levels are repelling each other, a la Coulombs Law, it is easier to remove a valence electron from a 5th energy level because it's going to have 1, 2, 3, 4 layers of electrons repelling it, a la Coulombs Law. Okay. Ionization energy, again, you have to talk about effective nuclear charge and shielding effect. I kind of just touched on this. What about second and third ionization energies? This is where you're taking from the second electron or possibly a third or fourth. Why would it cost so much energy to remove all of these electrons? I think I just paused. Did I just pause? There we go. Why would it take so much energy to remove sodium's electrons when you get to the second one? Again, its second electron isn't a valence electron. Its first electron is on the outside. It's 3s1, but the second one you want to take is a 2p. It's a core. And so you see that trend all the way down this entire group. As you go to take the first 2 for magnesium, it's pretty easy because they're on the outside, but the third one's a big jump. You're going to take 3 from aluminum, it's pretty easy, but the third one's a big jump. 4 from silicon, pretty easy. 5 from phosphorus. And you kind of see that trend all the way down. It is a huge jump as you get to the core electrons. The valence electrons have, for this particular period, they have 1s, 2s, 3s. They have the 1s, 2s, they have 2 energy levels repelling them. But once you take those valence electrons off, you're starting to dip into the core, which is why you see this huge jump in the cost to take electrons. So first ionization energy increases as you go across a period because there's a higher effective nuclear charge. First ionization energy decreases as you go down a group because there's an increase in shielding effect. Make sure you understand those terms very clearly. I don't like electron affinity. It's the amount of energy associated with an electron being gained. You really just need to know the term. It's the amount of energy associated with the addition of an electron. So imagine you're being given something and you're happy that you got it. It's like the joy you express when you receive the thing you're attracted to. And I say that attraction because the protons are pulling the negative electrons in and they're attracted to them. And it's a release of energy as the electrons are added. The trend is pretty ugly. It doesn't work too terribly well. It kind of jumps back and forth, back and forth, back and forth. It's ugly. We don't usually try to explain the trend. We just talk about the term and how it's the energy associated with the addition of a new electron. Here's a diagram that shows you ionic radius. In your notes, I did say the lighter area represents the atom's original size. In here, it's the red or the blue. The red is the original the ions. The color would you say olive? The greenish brown olive color is the original size, and the red or blue is the ion size. On the left side with the red ones, those are all metals that are losing electrons, which is why the size gets smaller when it turns to red, because they're losing electrons. On the right side, we have anions that gain electrons, so the original size is smaller, and then boom, it gets bigger as it gains electrons. Let's kind of focus in on NOF for a second and look at the larger size. You know, fluorine has 9 electrons, it gains 1, it has 10. Oxygen has 8 electrons, it gains 2, it has 10. Nitrogen has 7 electrons, it gains 3, it has 10. So all 3 of those have 10 electrons, but their sizes are not the same. While they have 10 electrons, they don't have the same number of protons. Of the 3, fluorine has the most protons, so the Coulombic attraction between its 9 protons and the 10 electrons is greater than the Coulombic attraction between nitrogen's 7 protons and its 10 electrons, which is why, since there's a greater attraction for fluorine, the size is smaller. There's a lesser attraction for nitrogen, so its size is bigger. Even though it's the same number of electrons, there's not as much pull, or there's more pull, depending on how many protons there are. Put these in order. It's not too hard. You kind of look at their position. As you get closer to helium, they get smaller because you have a greater effective nuclear charge, and you have fewer energy levels, so less shielding effect. With B, you do have to be careful that you have the calcium ion has lost 2 electrons. You have to properly compare. This is the last piece. I almost did it in 20 minutes. Make sure you talk about how metal ions lose electrons, so their ions are smaller. Anions or non-metal ions gain electrons, so their size is larger. You have to talk about how the protons to electrons have changed. And I think that's about it. Make sure you really thoroughly understand effective nuclear charge, how many protons are in the nucleus as compared to the shielding effect. And that you understand shielding effect. The shielding effect is the number of energy levels on the inside repelling the outside.